Local compactness. A topological space X is said to be locally compact at a point small x element of capital X if X has a compact neighborhood in capital X. We also say that the space X is locally compact if it is locally compact at every point. Proposition: if the space X is regular and locally compact at a point small x element of capital X, then small x has a local base consisting of compact neighborhoods. We need to assume that the space is regular and locally compact at the point small x. We will have to prove the existence of a local base of the point small x which consists of compact neighborhoods. Assume that the space X is locally compact and regular at the point small x. Since the space is locally compact at the point small x, the point X has a compact neighborhood, say C, in the space X. Now, to prove the existence of local base consisting of compact neighborhoods, we will need to show that for any neighborhood of small x, there will exist some compact neighborhood of small x which is contained in the previous neighborhood. Let us consider an arbitrary neighborhood, say U. Since the space is regular, there will exist a closed neighborhood, say capital M, of the point small x such that capital M is contained in U. This is obtained from a characterization of regularity. Here both M and C are neighborhoods of the point small x. Hence, their intersection M intersection C is also a neighborhood of the point small x, and since M is contained in U, M intersection C is also contained in U. Since M is a closed subset of the space X, M intersection with C is a closed subset of C. Since C is compact, M intersection C, being a closed subset of a compact space, is compact. If M intersection C is compact in the subspace, then M intersection C will be compact with respect to the topology on X also. So, we have obtained a compact neighborhood M intersection C of the point small x. So, we can conclude that the point small x has arbitrarily small compact neighborhoods in the space X, or that such neighborhoods forms a local base at the point small x. In the next proposition, we will be replacing regularity by Hausdorff property. Assume that X is Hausdorff and locally compact at the point small x, then the family of compact neighborhoods of small x is a local base at small x. Proof: assume that the space X is Hausdorff and locally compact at the point small x. Then, as the space is locally compact at the point small x, the point small x has a compact neighborhood, say C, in the space X. To prove that the family of compact neighborhoods of the point small x is a local base at small x, we will need to consider an arbitrary neighborhood and we will have to find a compact neighborhood contained in it. Let us assume that U is an arbitrary neighborhood of our point small x in the space X. The set C in its relative topology is a compact. Since we have assumed that C is a compact neighborhood, it is definitely a compact subset, and since the space X is Hausdorff, this subspace will be Hausdorff, as Hausdorff property is hereditary. Thus, the subspace C is a compact Hausdorff space, hence C is regular. Now we have two neighborhoods C and U. So C intersection U is a neighborhood of the point small x in the space X. And so C intersection U is a neighborhood of the point in the subspace C also. Since C is a regular space, by a characterization of regular spaces, there exists a closed neighborhood, say D, of the point small x in the subspace C, such that D is contained in the neighborhood C intersection U. Here note that D is a closed subset of the compact set C, hence D is also compact. Moreover, C is a neighborhood of X in the space X. D, which is a neighborhood of the point small x in the space C, will be of the form some neighborhood of small x in space X intersection with the subspace C. Since C itself is a neighborhood of point small x in capital X, this is the intersection of two neighborhoods of small x in the space X itself. So this intersection will also be a neighborhood of small x in capital X. So D is a neighborhood of the point small x in space X also. That is, D is a compact neighborhood of small x in capital X. And we have obtained that D is a subset of C intersection U, and we know that C intersection U is definitely a subset of U. That is, we have obtained a compact neighborhood D of the point small x in space X such that D is contained in the neighborhood U. Since U is arbitrary, this implies that the family of compact neighborhoods of the point small x is a local base at small x. This completes the proof. Corollary: every locally compact Hausdorff space is regular. Suppose the space X is locally compact and Hausdorff. Let small x be a point of the space X. Then by the proposition above, as the space is both locally compact at X and Hausdorff, we can see that the family of compact neighborhoods of small x is a local base at small x. But we know that in a Hausdorff space, every compact set is closed. So we can say that the family of all closed neighborhoods of small x is a local base at small x. By a characterization of regular spaces, this will imply that the space X is regular as required. Thus we can conclude that every locally compact Hausdorff space is regular. Proposition: an open subspace of a locally compact regular space is locally compact. For the proof, let us assume that X is a locally compact regular space and suppose that capital Y is open in the space X. Let small y be an arbitrary point of capital Y. Then since capital Y is open in X, capital Y is a neighborhood of small y in the space X. Since the space is locally compact and regular, by a previous proposition, this space will have a local base at the point small y, which consists of compact neighborhoods. Let C be a compact neighborhood of the point small y such that C is contained in y, but capital Y is locally compact at small y from the definition of local compactness because of the existence of a compact neighborhood contained in y. Since the point small y is arbitrary, we can conclude that the space y is locally compact at all points, and hence the space y itself is locally compact in the subspace topology on it. Proposition: let X be a Hausdorff space and Y a dense subset of X. If Y is locally compact in the relative topology, then Y is open in X. To prove that Y is open in X, we will need to show that Y is a neighborhood of each of its points. So, for the proof, let us consider an arbitrary point, say small y of capital Y. Since the space Y is locally compact, it will be locally compact at the point small y also. So, there will exist a compact neighborhood of small y in capital Y. Let C be the compact neighborhood of small y in capital Y. Since C is a neighborhood of small y in the subspace Y, C is of the form D intersection with Y, where D is a neighborhood of small y in the space X. Let G be the interior of D in the space X. Then since D is a neighborhood of Y, Y is an interior point of D. So, Y will definitely belong to the interior of D, that is the set G. We claim that G is contained in Y. To prove this claim, first we show that G is contained in G intersection Y closure. To prove this inclusion, let Z element of G and H is any open neighborhood of Z in X. Then to prove that this Z belongs to G intersection Y closure, it is enough to show that every neighborhood of Z intersects G intersection with Y non-vacuously. That is, it is enough to prove that this arbitrary neighborhood H intersects G intersection Y non-vacuously. Then G intersection with H is a non-empty open subset of X, since both G and H contains the point small y. So, G intersection H will contain the point small y. So, it will be non-empty. Since G is the interior of D in X, G will be open in X. Since H is open, the intersection G intersection H will be an open subset of X. Now, since Y is dense in X, every non-empty open set in X must intersect Y. Therefore, the non-empty open set G intersection H intersection with Y also should be non-empty. That is, G intersection Y intersection with H is a non-empty set. Since capital H was arbitrary, we can say that every open neighborhood of Z meets G intersection Y. Therefore, we can say that Z will belong to the closure of G intersection Y. Therefore, we have proved that G is contained in the closure of G intersection Y. Now, G intersection Y is a subset of D intersection with Y since G is contained in D. Since we had defined G as the interior of D, so G will be a subset of D. But we know that D intersection Y is equal to C. Thus, we have obtained that G intersection Y is a subset of C, where C is a compact subset of the Hausdorff space X. Therefore, C is closed in X. Therefore, G intersection Y contained in the closed set C will imply that the closure G intersection Y closure being the smallest closed set containing G intersection Y will be contained in C. And we know that C is a subset of Y. Thus, we have G is a subset of the closure of G intersection Y. G intersection Y closure is contained in C and C is contained in Y. And this will imply that G is a subset of Y, as we had claimed earlier. Thus, we have shown that Y contains an open neighborhood of each of its points. Therefore, Y is open in X as required. Theorem: a subspace of a locally compact Hausdorff space is locally compact if and only if it is open in its closure. For the proof, let us assume that X is a locally compact Hausdorff space and that Y is a subspace of X. For convenience, let us put Z equal to Y closure. We will need to prove that Y is locally compact if and only if Y is open in its closure Z. Since local compactness is weakly hereditary, Z being the subspace of X is locally compact as Z is closed. Also, Z is Hausdorff since Hausdorff property is hereditary. Thus, Z is a locally compact Hausdorff space and hence it is regular by a previous proposition. We know that from a previous proposition, an open subspace of a locally compact regular space is locally compact. Here, if Y is open in X, then Y will be an open subspace of the locally compact regular space Z. So, Y will be locally compact. Conversely, if Y is locally compact, then as Z is a Hausdorff space and Y is in fact a dense subset of Z, which is Y closure. By the previous proposition, we can conclude that Y is open in Z, that is Y is open in its closure. This completes the proof of our theorem. Assignment: prove that local compactness is preserved under continuous open functions and also that it is a weakly hereditary property.